In this video, we'll discuss alternative evaluation strategies. So an evaluation strategy determines when a function's arguments are evaluated, and sometimes what kind of information gets passed into the called function. So we just seen one type of strategy. In the previous video, we saw what was known as applicative order evaluation. We didn't call it that, but that's its name. And for contrast, we'll consider another one here called normal order evaluation. So applicative order evaluation, sometimes called eager or strict evaluation, this is the rules of scheme's general rule of evaluation. It's what we just learned. The basic idea being we need to evaluate all of the sub-expressions before we take that apply step. So at the point that we do apply, there should be no nested combinations left. We should only apply the value of a procedure to the value of its arguments. Okay. So for example, if we have some function double here, and we say, what's the value of double times 3, 4? Well, before we can figure that out, before we can apply this function to its argument, we have to find out what's the value of that argument. So we say double, and then times 3, 4 is 12, so now we have double 12, and then it runs through the body. We substitute 12 in for the parameter, and then we have plus 12, 12 to get 24. Okay. So for applicative order, we evaluate the sub-expressions before we do the substitution step. Now, by contrast, normal order evaluation, sometimes called lazy or non-strict evaluation, is kind of evaluation that you find in the lambda calculus, which you might recall is the origin of functional programming. And other early variants of Lisp also contain normal order evaluation. You also find it in the modern language Haskell. So the rules for normal order evaluation is we start by evaluating the leftmost sub-expression. So if we have prefix notation, the leftmost sub-expression is just going to be the operator. And then if the value is a primitive procedure, so if the thing that we evaluate is like a plus or a times or some sort of built-in operation, then we'll just evaluate the other sub-expressions, kind of like we did before, right? We can't do addition until we have numbers, so we'll have to reduce these combinations to turn them into numbers. But if when we evaluate that leftmost sub-expression, if it's not a primitive procedure, so if it's a compound or user-defined procedure, then what we'll do in normal order evaluation is we'll apply it to the unevaluated operand sub-expressions. Okay. So normal order will only evaluate the sub-expressions when they're needed. So first off, we evaluate the leftmost to figure out what sort of procedure we're dealing with. If it's a compound procedure, that's all the evaluation we have to do for now. We just move straight to the apply step. Okay, so for example, if we have some function double and we want to apply times 3, 4 again, so we want to evaluate this combination. With double, we first evaluate the left side here. We find that it's a compound procedure, so we just do the apply step right away. So we take the argument here, unevaluated, and substitute it for its parameters in the body here. So it would be plus xx would be the body of double, wherever we defined it before. Now it becomes plus times 3, 4 plus times 3, 4. So notice we didn't evaluate that times 3, 4 down to becoming a 12. Is just times 3, 4 as it is. Right, then once we've evaluated that, or once we've done that substitution, we can evaluate the combination. So now we have the symbol plus, which is a primitive operation. We can't do that operation until we have the values of these other combinations here, these other sub-expressions. So then we start to evaluate. Left to right, times 3, 4 gets 12, times 3, 4 again gets 12, and then we get the same answer, 24. So in these cases, it doesn't change the meaning, it's just the order of evaluation that changes. And let's take another look at another example here. So we saw in a previous video, we saw this example here, substitution model for f of 5. Actually, let me grab the code for that as well so we can see it. Here's some functions from the previous video. Let's put these at the top of today's code as well. Okay, so a substitution model for f of 5, where f of a is the sum of squares of plus 1a and times 2a, where sum of squares is the sum of the square of x and the square of y for two parameters x and y, and square is times xx. Okay, so we saw the substitution model, which follows the general rule, or now we can call it applicative order evaluation. We pass in 5 into f, so we do that substitution. So we have the body of f, where a has the value 5. And then before we can apply this sum of squares procedure to its arguments, we need the values of those other sub-expressions. So we get plus 5, 1 becomes 6, times 5, 2 becomes 10, and then we can do the application step where we move into the body of sum of squares, so plus square x square y, where x is 6 and y is 10. And that gives us that line, and then we reduced from there substituting square to become times 6, 6 and times 10, 10, and then just arithmetic till we got to 136. Okay, so we saw all that, and if you want to walk through previous video, you can go back to that one. But let's see what this looks like in terms of normal order. So this is the substitution model using applicative order evaluation. Let's do the substitution model using normal order evaluation. Okay, we'll use the exact same expression though, so f of 5. Now, with normal order, it says start with the leftmost sub-expression, so in this case it's the function f, and determine is this a primitive operation, or sorry, first off we want to evaluate it, and if we want, let's run our code here so we can see what the value of f is. It's the procedure f, okay? So we get this procedure object. And if it's a primitive procedure, we can just do the apply right away. Or sorry, if it's a primitive procedure, we need to evaluate the remaining sub-expressions. But because this is a compound procedure, we can just do the apply right away. As it turns out in this case, the argument is a primitive value, so it doesn't actually make a difference. It's going to look the same no matter what step we took here. So the next step says substitute 5 into the body of sum of squares like we've done before. So there's our sum of squares where a becomes 5. Oops. Okay. And this is where they differ. So with applicative order, before we can apply sum of squares, we had to figure out what's the value of these two expressions. With normal order, because this is a compound function, a user-defined procedure we can call it, what we'll do is we just apply that to its arguments without evaluating those arguments. So we take the body of this procedure, and everywhere where there was an x, we put plus 5, 1. And everywhere where there was a y, we put times 5, 2. Okay. So notice our expression is expanding and expanding here, but we can keep going. So the next step says, again, evaluate the leftmost sub-expression, which is always going to be the function or operation in a well-formed expression. In this case, it's the plus operation, which is a primitive operation. So primitive operation says, well, I can't do this operation until I have the value. So I can't just do the application step. I now need to evaluate the next two sub-expressions. Now, the order of that evaluation is not super important. Just like when we had applicative order, if these sub-expressions are independent, that is, say if their value isn't dependent on one another, which you can basically tell by the brackets close before it reaches the next sub-expression there, then we can evaluate them at the same time. We did that exactly that in this applicative order. We said square 6 becomes times 6, 6, and square 10 at the same time becomes times 10, 10. If you want, you can go left to right the way the interpreter on a serial machine would, but you can do it either way in the substitution model. So let's go through this one a bit slow just to be safe. So we have the plus symbol, and in order to apply that to its arguments, we need to figure out what is the value of those arguments. So to find the value of this expression, we start with the leftmost sub-expression, which is the compound procedure square. And because it's a compound procedure, we'll just apply it right away to its arguments. So the body of square is times xx, which we can put in here, where x is the unevaluated plus 5, 1. So that gives us that first sub-expression, and then for now we'll just leave square times 5, 2 as it is. Close that and close the plus. Okay. So notice this plus 5, 1 from SOS went into the body of SOS, and now it's into the body of square as well. So moving from left to right, so plus, before we could get that, we still needed the sub-expression. That sub-expression has expanded a bit now, but it has expanded into primitive combination, or primitive operators. So we have times. In order to evaluate that, we need to evaluate its sub-expressions, which is plus 5, 1 and plus 5, 1. So again, because we have primitive operators, we can apply them right away if we have primitive values as well. So we can say plus times, at this point, because this is a primitive operation, we need the values of its sub-expressions, so this becomes a 6 and a 6. And over here, we haven't even looked at this square yet, times 5, 2. Close and close. Okay. And we keep going. So this multiplication now has primitive values, so we can apply it. So we have plus 36, and then square times 5, 2. All right, and then to apply this square to figure out the value of this sub-expression, we do the same thing we did before. We apply the function, because it's a compound function, directly onto its arguments without any evaluation. So we'd say 36, then the body of square, which is times xx, where x is times 5, 2, times and plus. Okay, and now we just have arithmetic, so we can just collapse the whole expression. 36 times 10, 10, plus 36, 100, and then 136. And notice again, we got to the exact same answer, just in a different order of expression. So, with normal order, when we have a compound operator or a compound procedure as the operator in their combination, what we do is we apply it directly onto its arguments without having to evaluate them first. So SOS takes in plus 5, 1 without that becoming a 6 first, and then inside the body it's plus 5, 1 still. Now, in this case, I went left to right through all of these things, and I say evaluate the first symbol, determine is it a primitive or not, and then determine from there, do we apply or do we have to evaluate? And I said we could leave this square to the end, but we don't have to. I'll just run through this real quick using it, essentially doing things in parallel when possible. So we had sum of squares becomes plus 5, 1 times 5, 2, well, 5, 2. And then that becomes, we apply sum of squares onto its argument, so we had plus square plus 5, 1 square times 5, 2. Okay. And at this point I said, well, let's just go left to right and do it the way the interpreter does it. But if we want, we can do it in parallel as well. So square becomes what it becomes here, times xx, where x is plus 5, 1. And then this square can, at the same time, without any loss of information or without any ambiguity, can become times 5, 2. And then the whole thing can be reduced as well. So if you feel up to the challenge, you can do everything in one large step. I recommend taking things slowly, especially at first as you're getting used to these things. That way you won't make as many mistakes. There's times 6, 6. And this becomes times 10, 10. That can be done in parallel as well, so essentially collapsing all of these primitive combinations here. And then plus 36, 100, plus 136. Oh, sorry, not plus, just 136. So same answer. In this case, we just did things in parallel to shorten the amount of typing that you have to do. Either of those is allowed, so long as when you're doing normal order, you apply compound procedures to their arguments without first evaluating the arguments. Applicative order, we first evaluate the arguments, and then we do the application step, the substitution. Okay, so normal order and applicative order are two of many different types of evaluation strategies. The only two that we'll cover in this course, but you'll run into others as you go throughout the course, or throughout your careers as computer scientists, many different languages. But with these two, they're both important in terms of functional programming, in part because normal order was the sort of default, sort of a happy accident was the reason normal order was used as a default when Lisp was first invented. And applicative order is a more familiar type of evaluation order. Now, as we've seen, they both give the same results so long as our code has no side effects, so long as we are dealing with a purely functional expression with pure functions that don't alter the values of existing variables. But applicative order, as I said, can seem more natural. It works a lot more like arithmetic, where before we do this function, we need to figure out what are the values of that function. It just seems sort of how we typically think about these combinations anyways. Applicative order also has some advantage in that it can avoid some repeated evaluations. So if we notice down here in the substitution model for, let's say, of square, we had times xx, where x was plus 5, 1. Now you can imagine if we passed a value into square that wasn't just a single addition, if it was this very large computation, well, that very large computation gets doubled inside the body of square. Because it's unevaluated, it'll get passed into square, it'll get substituted for both instances of the symbol x, and then both will need to be evaluated. And it's possible you could come up with an interpreter that intelligently predicts that, okay, I've already evaluated this once, I can memoize that it has this value and save it for later. But in a very naive approach, the normal order evaluation can run into some extra work by having to evaluate the same combinations of symbols if that symbol gets used multiple times in a body of a function. That's not to say that applicative order is always more efficient, though. Normal order can also be more efficient in certain situations, specifically if a piece of code is completely unnecessary. So let's say, for example, in the body of sum of squares here, we passed in two combinations, x and y. So we had +5, 1 for x and -5, 2 for y. It's conceivable. We haven't run into the specific code that will allow us to do it yet, but we could imagine that there's a branch in this code where we only ever need the square of x or the square of y, but never both. In applicative order evaluation, we're going to evaluate both of those things, the value for x and the value for y, before we do that substitution. In normal order evaluation, if we never need the value for x or the value for y, then it will never get evaluated, and we'll save all of those cycles. So if we have unused code, then normal order can save us some time there. Now, one of the issues with normal order is that it does require a bit of extra overhead. It requires some sort of mechanism in order to maintain these combinations as unevaluated. Whether we're just moving symbols around, if symbols become a part of our code, if the code is a data type itself, or if we have some sort of extra construct like a thunk, which is a function that doesn't take in any parameters, and uses that to contain all the code. We'll deal with that later on in the course, though, once we come back to creating lazy operations. But for now, just keep in mind that nothing is free. If we want to maintain these combinations as unevaluated combinations, then we need to maintain that status of unevaluated as we pass the combinations through, so that the interpreter knows that this thing, before we try to use it as a value, needs to still be evaluated. All right. So there's a bunch in this chapter and in this video. First off, Scheme uses applicative order evaluation. It might be a bit strange that normal order is called normal order, even though it's no longer the normal type of evaluation. It's now a bit abnormal, if you will. Scheme uses applicative order, and it's somewhat common from other languages that you might have seen before as well. But evaluation in all functional languages is just substitution. We take the symbols that we have here, we substitute them into the body of our function, wherever the body of this function is. There it is. Take the symbols of our arguments, we substitute them into the body of our function where the parameter symbols were, and then reduce from there. So evaluation in any language is just this algorithm, eval apply, and now we've looked at it very closely to see what the specific algorithm in Scheme is. That's all for this video. In the next video, we'll take a look at conditional expressions in Scheme.